Huh. All right. Well, I guess I better share a screen. I'm still recording. Oh, can you hear me? Cool. Well, welcome everyone in person. We don't have to do this every time, but may as well the first day, at least first day back. Here is just, if you haven't, I guess, have you two, you're Dennis and, I'm sorry, what's your name again? Abel and Rhiannon, can you show your, here's mine, you can see it's green, you can see the screen, green. The Lumicite. Okay, that's good. Yeah, no, it's just, it's easy to see because it's either green, yeah, you're good, or it's red. Yep, good, okay. But, okay. And in person again, sometimes this screen turns kind of yellow, but does let me know I just have to jiggle this thing here. So, well, anyways, weird being back. I like teaching in person better than Zoom. I'm weird. I like asynchronous and I like in person. I just, for whatever reason, I hate Zoom teaching. Or what do you guys like, do you like Zoom learning, or obviously not because you're here? So do you guys like asynchronous, or is it just, is that, no, you don't? Yeah. The only thing I'm miss about this is I probably could be doing my laundry right now. So I'm significantly less productive. That's just one of the small things that brings me joy for whatever reason. I just like to do my laundry during class. So, but oh well, I'm just being silly. But do you guys have any other things that you do via Zoom? We do like all our faculty meetings by Zoom now. Or is that, I'm okay. Huh. I mean, I'm married, so I'm out of the game, but I mean, do people like do dating on Zoom now, or like okay. All right. I didn't know. I was just like, what do people do in this day and age? Oh well. But anyways, okay, well, I better stop talking about society and go back to chemistry. Anybody have any questions about anything? Question before I came in, we're not going to cover X-ray diffraction. There's just a lot of material, and I'm not going to cover everything that's in the book. And if you have any questions about it, let me know. So, but any other questions? Oh, I'm also, I know that I originally had the test, I think, due Wednesday. I have it set up to accept late work, but I want to extend it another week. Do you want me to actually change it in mastering so you feel better, or are you okay with just it being overdue and you get credit for it anyways? Yeah, because I know I'm probably not going to finish the material till Wednesday. I like to give it a week to sink in. So, but what I mean is like the way I learn, me personally, I kind of learn something, then I kind of like think about it like subconsciously in my mind. Sometimes I even dream about it, kind of thing, and then it kind of makes sense about a week or so later. So that's just myself. And if you're ready right away, go ahead and take a test. Or if you need more time, I'll bug you. But what I mean by bug you is I see myself as a coach, and like if you miss a deadline, I'm going to write you and see if you're okay. And if I write you, you're never in trouble. It's just kind of like, what's going on, kind of thing. And unfortunately, I found that's a lot of time that people tell me that they're like having issues with stuff, and then we can get you help. So, but anyways, hopefully that's not what's going on. And of course you're here, so things are probably doing well. So, all right, where we left off last time, I was kind of jumping ahead and talking about thermodynamics and how Gibbs energy works, and how the relationship between enthalpy, which is kind of the heat of reaction, the bonding, and entropy. So entropy is disorder. And that also, when it comes to like water and oil, actually oil loves water, but in order for water and oil to dissolve each other, oil has to get between itself, an oil molecule has to get itself between the hydrogen bond network of water. And water doesn't like that, and the water actually literally pushes it out of the way. And then the oil then just floats to the surface because of gravity. But that brings about some solubility rules. And the general rule is like dissolves like, meaning that polar molecules and or some solids will mix together. I'm sorry, as far as a liquid phase. So we're talking about solutions, and there are many different types of solutions, gaseous solutions, solid solutions, but usually when we say solutions, we mean liquid. And you can get polar things like alcohol dissolve in water, and you can get some solids like salt to dissolve in water. And nonpolar will mix with a nonpolar molecule. So gasoline and oil will mix, for instance. But you can't, it's really hard to get polar and nonpolar compounds to mix together. So things like olive oil or any oil in general, and vinegar. So like vinaigrette salad dressing. I mean, if you notice before you put it on your salad, you have to like shake up the bottle to mix it up. And then after some time, it just separates, right? So you got to give that time, the water and the vinegar, the acetic acid to push the oil out of the way, and then gravity take hold. Okay, so why do we care? Because of vitamins. So vitamins, so as I talked about last time, we have macronutrients. So our true macronutrients are oxygen and water. So I got about water today. So those are our true macronutrients, but we also need, and quite a bit as humans, carbohydrates, fats, and proteins. Those are our macronutrients. So, and we have micronutrients, which are vitamins and minerals. And vitamins are organic molecules, so carbon-containing molecules, and minerals are elements other than carbon, hydrogen, oxygen, nitrogen that our body needs in small amounts. So, and vitamins, so if you want to know the etymology of the word, it used to be vital amines. So an amine is a molecule, an organic molecule that has nitrogen in it. So vitamin B5, for instance, here, this is an amine. So, but we found out that, and we thought that they were all vitamins were amines that are vital, but it turns out not all of them are amines. So what we did is just said it real fast. I said vitamins. Instead of vital amines, it's vitamins, or vitamins if you're from Great or whatever UK, and they all do something. So, and unfortunately, when it comes to vitamins, we only really know deficiency diseases. It's hard to say how many vitamins do you need, and so it really depends. And deficiency diseases. So vitamin A, for instance, this one here is retinol. So, and the ol, so this is retinol, and the OH means alcohol. So this is an alcohol. So, and you can learn about this more in organic chemistry. And if I said the word retina, what part of the body do you think of? Yeah. Okay, yes, you're pointing to your eye, yes. So what vitamin A does, among other things, well, vitamin A is an antioxidant. So what is an antioxidant? It's a reducing agent. So, and our primary antioxidant is actually vitamin C. But I'll get to vitamin C in a second. But lack of vitamin A, if you don't get enough vitamin A in your diet, you get night blindness. So you can't really see at night. So that's a deficiency disease for vitamin A. Vitamin Bs, and there's a whole bunch of them. There's not just one, there's several. Not going over all of them in depth. They kind of help us process energy and make our nerves work well. That's kind of what vitamin Bs do. It's kind of energy and nerves kind of thing. And vitamin C is our primary antioxidant. Vitamin D helps. Okay, and so lack of vitamin Bs, let me go back. Depends on which vitamin B. Various vitamin Bs, you kind of get sluggish. Without vitamin Bs, you get sluggish and your brain and memory doesn't work. And like I said, it depends on the vitamin Bs. I'm just going to go over quickly. Vitamin C, lack of vitamin C causes a condition called scurvy. Scurvy is a condition where your teeth can fall out and you have scaly skin. And vitamin C is also known as ascorbic acid. So ascorbic anti-scurvy acid. So I mean, the names, right? So I guess I go into some of the names. So vitamin C is anti-scurvy acid. Vitamin D is, well, it's calciferol. It's, do they have D here? No, we don't. Vitamin D deals with your bones, helps you uptake calcium and magnesium in your bones. And lack of vitamin D causes a condition called rickets, where your bones get really bendy. And vitamin E is, it's a fat soluble, I'm jumping ahead. It's a fat soluble antioxidant, and vitamin E is going to give you similar symptoms of vitamin C, lack of vitamin E. And then vitamin K, lack of vitamin K causes hemorrhaging. So vitamin K deals with coagulation, helps your blood coagulate. So vitamin K is actually one of the few that you can overdose on. So you can overdose on vitamin A. It's really hard to, you can overdose on anything. You can overdose on oxygen, right? But it's really hard to overdose on vitamin C, really hard to overdose on Bs, really hard on E, really hard on D. You can't overdose on K. So the ones that are kind of dangerous are vitamin A and vitamin K. Vitamin K, if you take too much vitamin K, it turns your blood into something of the consistency of cake batter, and it makes it, and your blood pressure drops. At the same time, vitamin K is used in an emergency situation. Say someone is hemorrhaging or is about to bleed out, you can give that person a mega dose of vitamin K, and that might save the patient's life, because then it just congeals the blood real fast. So, but let me start with vitamin C. And vitamin C, well, I told you it's an antioxidant. So you guys are relatively young. So let's say you came into class today really, really hungry, and I had a bunch of Brussels sprouts sitting in the front row. And you're really hungry, and you're like, boy, I really want to eat those Brussels sprouts because I'm really hungry. What's a way that I could prevent you from eating the Brussels sprouts? Like, what if I took a bunch of Halloween candy and stuck it in front of the Brussels sprouts? Are you gonna be like, either I can eat the Brussels sprouts or I can eat the Snickers bar. Which one do I choose? You're probably go for the Snickers bar, right? So how do you prevent a very reactive molecule, like a free radical, like a molecule has an unshared pair of electrons? How do you keep that molecule from attacking an important molecule like DNA? Well, you put vitamin C in front of the DNA, and that free radical molecule will go after the very tasty looking reducing agent, vitamin C. And then once it gets destroyed, it's no longer reactive, the DNA is safe, right? So it's just like hungry students not eating Brussels sprouts because there's lots of, I don't know, Halloween candy in front of it. So that's the way that antioxidants work. So vitamin C and vitamin E work that way primarily. Vitamin A, to some extent, it's an antioxidant, but we also use vitamin A for different molecules. But vitamin C, anti-scurvy acid, so ascorbic acid, and generally speaking, things tend to be either polar soluble, we also say water soluble, or non-polar soluble, and we say fat soluble, and or hydrophilic. So phila means like, hydrophilic, water loving, those are water soluble. There's also hydrophobic. Hydrophobic means water hating, and fats tend to be hydrophobic. Then there's lipophilic, so fat loving, those are non-polar, and lipophobic, those tend to be water soluble. So generally speaking, things tend to fit in one category. There are a few cases where something fits in both. Ethyl alcohol, the alcohol that's in alcoholic beverages, that actually can dissolve in both fats and water. but it's more of an exception to the rule. Things tend to fall into one category. But vitamin C, and you won't be required to do this though, but to the extent, vitamin C, you can see here, there are 4 OH groups. And these 4 OH groups means that there are sites where it can hydrogen bond. And because there's so many of these OH groups, that means vitamin C is water soluble. So vitamin C is one of those vitamins that we need every day. So we're also higher order organisms. Many organisms can make their own vitamin C. Humans cannot. So we more or less have to have, we're omnivores, and I don't know if there's any vegans in the room. We actually do need meat. We can survive without meat, but it's really hard. So we need the, humans need the iron, and we need the B12. That's a lot of vegans have that issue. So if you do decide to go vegan diet-wise, you might have to supplement your diet with extra whatever supplements. So mostly iron and B12. And you also, it's pretty hard to get enough cholesterol. So we get most of our cholesterol from animals, and animals have cholesterol. So we use that as the basis to form many hormones. So it's best not to have a vegan diet till after puberty. So when you make all the hormones. So, well, I mean, you're still making hormones, but as you're growing, it's best to have ample access to cholesterol. But anyways, so vitamin C is something we need every day. And you ever see some of those stupid diets, like saying I don't know, maple syrup and lemon diets or something like that? They always, like the ones say, oh, you can lose 20 pounds in 5 weeks or something like that. Frequently, what they have is a source of carbohydrates and a source of vitamin C. So we need quite a bit of vitamin C. And vitamin C, we actually know a little bit more about. Most of the vitamins are from deficiency diseases. And the average adult needs about 60 milligrams, so milligrams, 60 milligrams of vitamin C to not get scurvy. So you need to have, on a daily basis, at least 60 milligrams. And it's hard not to. And surprisingly for Americans, one of the largest sources of vitamin C is potatoes. So potatoes have some, not as much as other things, but potatoes have a fair amount of vitamin C. So, but it seems that most adults do best with 200 milligrams vitamin C. The toxic dose for vitamin C is about 5 grams. But how are you going to get 5 grams of vitamin C unless you're just popping the pills from Costco? So I mean, the number of oranges and papayas they have to eat to get a toxic dose. The toxic dose just is from the acid. It makes your stomach kind of feel bad. So, but vitamin C, water soluble, and which also means our body doesn't store it. Here's vitamin K. And you can see here's the structure here. And so we haven't covered organic chemistry yet, but if you might see structures kind of looks like this. So when you have like two sticks, like if you just have a stick like that, this here, that equals an ethyl group. So the ethyl, I know I'm using all these terms. These are not necessarily needed for you right now, but in future classes, you might use this. Ethyl just means 2 carbon. And when you have the ball and this kind of ball and stick model, it means that every corner is a carbon atom, and you denote any other element besides that. And you also, you as the viewer, assume that the rest of the spaces are filled up with hydrogens. So you can draw vitamin K. You might see, like if you look it up on Wikipedia or something, you might see vitamin K like this. And they mean the same thing. So if you look at vitamin K though, there's no hydrogen bonding groups anywhere. And because of this, vitamin K is completely lipophilic, it's fat soluble, which means our body can store it. So that's a good thing. It takes some time to become vitamin K deficient. But also that because your body stores it, you can overdose on it. I told you it causes your blood to coagulate. And vitamin K, since your body stores it, it's actually a convenient way to kill yourself. So like vitamin K, you can get this in its pure form, but it's only offered by prescription. So, and if you ever look at vitamins, they usually don't put that much vitamin K in there. It's like 70% or like 20% in multivitamins. And the reason why is like, what happens if you take 5? You know, like they're kind of like, okay, what's a dumb person going to do? And take 5 vitamins, is that person going to die? And they kind of look at that, you know, okay, make sure you don't get too much vitamin K. Vitamin K, one of the ways that we do get vitamin K, we kind of can make it ourselves. So there's certain vitamins that are bacteria. So we have bacteria in our digestive system. We have bacteria in our digestive system that actually makes vitamin K for us. So it's an argument of, you know, do we really need this? But it's a symbiotic relationship that we have with bacteria. Biotin, it's a B vitamin, is another one that we make in our guts with symbiotic bacteria. But if you've ever taken like a long course of antibiotics, you might have to supplement your diet with vitamin K. Or the other thing you can do, so vitamin K by itself, but then there's something called a provitamin. A provitamin is something your body will turn into the vitamin. And you can take all the provitamin K you want. So our body only converts provitamin K to K, only what we need. So same thing with vitamin A, which I'll talk about soon. So provitamins, they're a bit safer. So you can take as many of those as you want, and spinach and green leafy things are full of provitamin K. So if you are taking a long dose of antibiotics, so if I ever do that, I always like, buy spinach and eat spinach. So just to make sure I'm probably overly cautious, but that's one thing you can do. If you know that you're going to be vitamin K deficient, you can just eat a lot of green leafy things. Here's vitamin A, also known as retinol. And so it has an OH group, but it has this really long non-polar group there. And because of that, even though there is this one OH group, vitamin A is lipophilic. It's not hydrophilic. It will dissolve in fats, not in water. And also, vitamin A is one of the things you can overdose on. So does anybody know the easiest source of vitamin A nutritionally? Not provitamin A. So it's polar bear livers. So believe it or not, polar bears, the big white bears, ice bears, they have a lot of vitamin A in their liver, and the Inuits and other Native American tribes up in Canada, they know to not eat the liver of a polar bear, because the liver will give you a toxic dose of vitamin A, and you will die if you eat polar bear livers. On the other hand, beta carotene, there is the molecule for beta carotene. It's 2 vitamin A's just joined together. If you imagine the OH being dropped, it's just 2 vitamin A molecules, and maybe you've heard of beta carotene. Oh, I've already put, I'll tell you, okay, beta carotene, vitamin A is fat soluble. Beta carotene is like completely fat soluble. There's no OH groups on it. And you can eat so much beta carotene that your fat turns yellow or orange and your skin turns yellow or orange. So there's actually conditions where people eat so much, like if you eat enough carrots, so you will turn yellow or orange depending on your complexion. And your fats, so if they dissect you and they look at your fatty tissues, because beta carotene is fat soluble, your fat will turn yellow and or orange. So, and that is completely safe. That doesn't bother us at all. So we can turn orange from beta carotene, but you eat 1 polar bear liver, you drop over dead. So kind of interesting. And here is vitamin B5. And you can see that there's lots of OH, and there's 1 NH group. There's 3 OH groups and 1 NH group. And that there's enough here that vitamin B5 actually is water soluble. So, and all vitamin Bs are water soluble. So, and it's really, really hard. You can overdose on vitamin Bs. but it's really difficult to do. Very, very difficult. You have to do it in vitamin B. Actually, you have to do like, you'd have to take like mega doses of vitamin B like once or twice a day for 6 months or more. And then start they actually changed the formulation on the 5-hour energy drink. Have you ever heard that before, the 5-hour energy? That people were taking several of those in a day, and some people started showing signs of vitamin B6 toxicity. And so they dropped the amount of vitamin B6 on that. So they had to change the formulation from, they just didn't expect people to drink like 5 or 10 of them a day for 6 months. And that's what people did. So, and then what happens with vitamin B6 toxicity, it's you start getting numbness in your hands and feet. So like I said, they changed the formulation. So for vitamins, vitamin C and B are water soluble. A and K are fat soluble. Vitamin D, E are also fat soluble. So our bodies store those. So anybody have any questions? I know it's a really brief thing talking about vitamins. You can take a course and learn all about them. Yeah. Oh, it's there is a derivative for that called retin A. Retin A is a drug, and it's from retinol. It's vitamin A, among other things, is an antioxidant. It's a reducing agent, and you can use other skin products that are reducing agents. Vitamin C, you can use a skin product, and vitamin E as well. Those are also antioxidants. So among other things, they prevent the attack, and they just like they clear up. And there's some other processes. So vitamin E, and also they're fat. I mean, they're oils. So they do certain things like they if you look at your skin, you have the protein keratin is your surface. So then on top of that, you have what's called the acid mantle, and that's that you have just a little. It's a water. It's an aqueous solution that's slightly acidic. Then above that, we have an oil layer that's primarily an oil called sebum. So, and when you disrupt those layers, you can damage your skin. And so, among other things, oils, they also they coat the top. They're called moisturizing, but they're moisturizing because they trap water in. And the antioxidants have the added benefit they can prevent certain conditions. Some things over time have shown that things like vitamin E can reduce scarring or heal scarring. So that's might happen, depends. That a combination of alpha or beta hydroxy acids. So it's a combination thing. Retinol, retin A, it's probably got some sort of, I'm not exactly sure what the exact mechanism is. It probably has something to do with the bacteria as well. Might kill some of the bacteria. There's a lot of other acne medications that kill bacteria. So, but does that answer your question, at least in part? Okay. Other questions? All right, and here's another molecule. So do you think this molecule here is water soluble or fat soluble? How many think it's water soluble? How many think it's fat soluble? So we got most going for fat soluble. This is in fact fat soluble. And the name of this molecule is lysergic acid diethylamide. Does anybody know what the common name for that molecule is? LSD, lysergic acid diethylamide. And it's fat soluble. So I mentioned vitamins. There's a whole nother category that we didn't talk about, drugs. Certain drugs are water soluble, certain drugs are fat soluble. And lysergic acid diethylamide, this is lipophilic, so fat soluble, which means, among other things, your body stores it. So probably the drug that your body stores the most easily and readily are cannabinoids, so cannabis. So many drugs are water soluble. So caffeine, alcohol, Other over-the-counter drugs, aspirin, they just go right through you. They go right through you without any issue. And then there's some drugs like lysergic acid diacylate. The other one is PCP. Both of these, more often PCP, your body stores these and you can lead to a condition called flashbacks. So, which means that if, like, can you imagine if you're, if you've taken LSD in the past and then later on you're on the treadmill and your body starts burning some of the fat, and then if you get enough, if you can release the drug back in your system from it's stored, and it might get to an effect that you can feel. So people feel that more frequently with PCP, actually. So that actually might be interesting because PCP, among other things, it releases your adrenaline. It opens up your adrenal glands. So it might be a performance enhancer, but it also, PCP is a dissociative anesthetic. I've never taken drugs, so I don't know. I've been high from like pain pills and surgery and that kind of stuff, but I've never taken any of these psychedelics, so I don't know. The dissociative anesthetics, ketamine is another one. Like, let's say that you break your arm. So pain management is how our drugs deal with a lot of. So you break your arm and you want to deal with the pain. Typically what you do is you take, we usually take opioids. And what opioids do is they increase the level of dopamine in your system. So dopamine is a neurotransmitter. So like if you pinch your arm, you're like, oh, my arm hurts, and like I'm pinching, and actually it doesn't hurt anymore. And now I just feel the pressure, and actually the pressure is lessening and lessening. I don't even notice it anymore. I haven't changed the pressure of my pinching in my hand. Dopamine is responsible for that. Dopamine stops the progression of nerve impulses. Like when you get dressed in the morning or something like that, you come out of the shower and you put your clothes on, you can feel your clothes going on. And like I now that I'm thinking about it, I notice my clothes, but can you imagine if you're all the time like clothes, wind, sounds, like every time your brain would explode. Dopamine is the way that we deal with that neurotransmitter wise. And certain drugs, alcohol is one of them. Although we're not entirely sure how alcohol works, but alcohol is a mild dopamine agonist. And other drugs really, really increase the amount of dopamine. So opioids are one. Cannabinoids can do it as well. So other drugs like cocaine, they do increase dopamine. They also increase serotonin. Serotonin is a happy chemical. It's kind of like sometimes called like, well, when you win something, you get excited. You're like, yes, got an A in chemistry, woohoo! Some of the good feelings are from serotonin. There's other ones. There's other drugs too, or other neurotransmitters as well, and a lot of them are used in combination. So sometimes oxytocin is called the hug chemical because like when you feel close to someone, you release oxytocin. You also release serotonin and you also release dopamine, but it's all of them in combination. So that's one way you can manage pain, is increase the dopamine in your system. Other one you can do is a dissociative anesthetic. So I break my arm and I take ketamine and or PCP. And what happens is that my brain still feels the pain. It doesn't connect the pain to a broken arm though. So it dissociates the sensation from what it means. And so a problem for things like PCP is that it also affects your adrenal glands. So people get they have a huge burst of energy and they can become violent. So, and there's another dissociative anesthetic, although it's not called a dissociative anesthetic. What is that stuff called? What is the sleeping? Gosh, I'm running out of brain power. Speaking of brains not working. Gosh, it's not, because we need Google. Sleeping medication, that's a dissociative anesthetic. It's gonna kill me when I see it. Not ketamine. It's not. Sleeping drugs. Sleeping pill types. Cleveland Clinic. It's gonna kill me when I see it. Sleeping pills. Hypnotic. Oh gosh, I forget the name. There is one. Come on, Google. Yeah, no, that's not supplement. Ambien, there it is. Ambien. I've never taken Ambien, but Ambien is a dissociative anesthetic. It works with your consciousness. You're not actually asleep, it just associates your consciousness. So, and although people, I said I've never taken it, but people have done weird things on Ambien. So, but but also with the solubility, so cannabinoids, and I like one of the ways they work is especially THC, tetrahydrocannabinol. It coats your nerve cells. Your nerve cells have synapses, so space between the neurons. And if you coat your nerve cells, the neurotransmitters as they travel between the nerve cells get slowed down by the THC. So certain things that people report, so like slowing of time, for instance, is from that effect of THC. It's just slowing down the neurotransmitters. And the other thing is with THC is that so local anesthetics, they tend not to work as well on chronic cannabis users because they don't dissolve the nerve cells as well. Oh, the edges of the nerve cells. So if you ever wonder, like if you go to the dentist and they shoot you up with lidocaine and how it doesn't hurt when they're drilling your teeth, it's because the nerves around and the edges of the nerves get dissolved. And then over some time they reform, but while it's dissolved, they just don't work. You can't feel anything. You can't move anything. You can't feel any pain. So that's how lidocaine works. So anybody have any questions in general about drugs or anything that? Nope. Okay, so here are some other solubility stuff. So miscible means it dissolves in any quantity. So if you see here methanol, so this is alcohols. Alcohol has and I know this is organic chemistry. You're not being tested on this, but our group is a alkyl or a hydrocarbon that's all single bonds. So hydrocarbon, hydrogen, and carbon. So methanol, one carbon is infinitely soluble in water. You can get a little bit to dissolve into so hexane here, it'll dissolve. It's kind of like gasoline. Gasoline is octane usually, but so it's fat soluble. So hexane is nonpolar. So methanol can dissolve a little bit into nonpolar, but not very much. Ethanol and also propanol, these two. So these will dissolve in any quantity into water and nonpolar. So they're kind of the exception to the rule. And then we have butanol. Butanol is not very water soluble, but it is soluble into lipophilic, and same thing with propanol or pentanol 5. So after 3 carbons, alcohols are basically fats. And why do we care? We're looking at alternative fuels to gasoline, and one of them we are actually looking at is butanol. So I know we're thinking about turning cars electric, but so if you ever look at some of these think tanks and some of the things that people put out for think tanks, and much of it has to do with life on the mainland. So if you've noticed, if you've ever driven in the mainland, there's an exit on the freeway about every 30 miles. And if there's not one, they tell you, like, next exit 80 miles, kind of thing. So, and the reason being is if your fuel light on your car comes up, you can usually travel about a mile, or well, I guess it comes down to the 2 miles. You can usually travel, 50-ish miles in your car when your fuel light comes on. And it's important to have an exit such that you can refuel your car. So, and we were thinking for a bit to use ethanol as a replacement. And problem with ethanol is, well, there's 2 problems. It's more reactive than gasoline. Gasoline's not very reactive. Octane's not very reactive. And the other thing is it has fewer calories, so it has less energy. So like what's going to get you, what's going to get you fatter? A pound of broccoli or a pound of chocolate? Obviously a pound of chocolate. Why a pound of chocolate? Because there's more calories, right? So what's going to get you further? A gallon of ethanol or a gallon of gasoline? Gasoline, why? More calories, more energy. So gasoline has about 2/3 the energy of gasoline. And so that's an issue. It's close, but that means if your car can go 200 miles on a tank of gasoline, it can go about 120 miles on a tank of ethanol. So that'll have to change the way we probably have to double the number of exits in the mainland. So for that, and with butanol though, this has about 90% the calories of gasoline, and then we wouldn't have to change our habits. So that was one of the reasons why, if we're really truly going to go all electric, we're going to have to also change our behavior, or at least change the infrastructure. So we have to put more charging stations. So, and what the think tanks are thinking about doing is finding a way to swap out cells. We're not set up for that now. I mean, the batteries in the car. The idea is that you go to a service station and then they they'll change the battery on your remote. Like if you have the AAA, AA, kind of batteries. So you open up the back and you whip out the batteries and you put new ones in. Maybe there'll be some sort of fuel cell, or not fuel cell, like fuel, whatever, battery transfer that you do at a service station now. Or they have more charging stations, and they do take time. So they can be pretty fast. But I mean, it's not going to be as fast as pumping liquid gas in. So, and then how far apart do we have them? So we like to use our existing infrastructure. So that's kind of stuff that we're thinking about right now for the future. But anyways, anybody have any questions about this? Okay, cool. Go on to the next topic. 14B. Okay. So let's talk about the physics of how solutions work. And I guess there's no Zoomers here, right? So I can come off and talk to the screen. Okay, so here we have, the solvent, which is the most, and the solute is what's dissolved. So we have pure solvent and pure solute. In order to get them to mix, you have to break the bonding in the solvent, and you have to break the solvents in the solute. Break the bonding in the solute, and then you got to mix them together. So this right here means you break apart the solute, you break apart the solvent, and when they mix together, so then there's the interaction between them. What happens if the enthalpy is lower than that? This is an exothermic process. It means heat will be evolved. And if it's less energy, this is endothermic. So the enthalpy is positive. The potential energy increases. So, and that probably looks a lot like the Born-Haber process from the previous semester. So, and if the solvent in the solute is much greater, then the solution definitely forms. So here's an example of some. So lithium bromide and potassium hydroxide, and I don't use these very often, but sodium hydroxide. So lye, LYE, lye. I make that in the lab all the time, and it gets hot. It gets really hot. So when you mix sodium hydroxide together, it gets really hot. And then if it's an endothermic process, the solution gets cold, and icy cold packs. If you ever sprained your ankle at a sporting event, that's what they typically use as ammonium nitrate for that. Ammonium iodide is another commonly one used. We don't use silver nitrate as much because it's expensive and it turns your skin brown. But more because it's expensive. These are endothermic, and they're entropy driven, but Entropy is what causes it to dissolve, but it gets cold. And then we have one, so sodium chloride is actually slightly endothermic, but they're about zero. I mean, they're close. They're close to zero. They don't really. You don't really notice it, right? You don't. At least I don't. When I mix salt and water, I don't notice the temperature going down. Also, sodium fluoride. When I brush my teeth, I don't like wow, I can really feel that 0.91 kilojoules per mole, the sodium fluoride. It's just there's not a lot of sodium fluoride in toothpaste. Okay. Next concept. And I know we jump around a bit. Any questions? I'm sorry, can you say it one more time? How do you determine if it's exothermic or endothermic? You can do it one of two ways. You can, I guess some of it is, you can calculate this out, the energy that it takes to separate the solvent and the solute, and then calculate the solution. And if the potential energy is lower than the original, then it's exothermic. If the potential energy is higher, it's endothermic. The other thing you can do is you can throw them together and see the temperature change. Right, so. Yeah, that's usually how, and that's classically how we did it. The quantum mechanics, we haven't been able to do, we started being able to do that since about 1960-ish, 70-ish. So, but in the 19th century, we could throw lye in water and notice it got hot. So, but yeah, usually it's done by experimentation. So, the questions? Yeah, please. Not necessarily that. So is the minty feeling cool? It's because that may not necessarily, because heat can also, when we say heat in food, that's actually pain. So that's more of our perception. And some of the things that we perceive are as a temperature change are not really our the true feeling. So another one is when you put alcohol onto wounds, you actually can feel a hot burning sensation, but that's the reason for that is because of the evaporation of the alcohol, not necessarily that's a temperature change. So some of those interactions you feel is more the perception of your nerves and how, and it's not a really true perception. As far as the cool food, I know what you're talking about, especially like if you eat a bunch of Altoids and you drink a glass of water, you're like, oh, it's cold, right? So I'm trying to think. That's gonna, I don't think it's gonna be a solubility thing because those oils and the water don't mix. Because that's got to be with the interactions with your taste buds and your nerves and how we perceive it. So it's going to be kind of a trick with our body perception, not a true temperature thing. So, other questions? But I don't know the exact process how because I know the oil, like methyl salicylate is that's going to be fat soluble, but the water and methyl salicylate is not going to mix, so it's got to be your nerves. But anyways, so the good, these are fun questions. I like these. So let's talk about here. We have sodium chloride, solid, and this means equilibrium. We have it dissolving in water, and it forms sodium ions and chloride anions, both in solution. So some terms. A saturated solution means no more will dissolve. So if you have a solution that cannot hold any more material in it, we call that saturated. It's completely saturated. Then we have unsaturated solutions, which means more can dissolve. And then we have supersaturated solutions where you up the temperature. So generally speaking, things dissolve better in higher temperature, with the exception of gases. So, but for salts, higher temperature means higher saturation because of the delta G is delta H minus T delta S. And remember, negative means it's going to go. If you increase the temperature, you increase that T delta S term, temperature times entropy term. And that means, and dissolving increases entropy. So higher temperature means, generally speaking, more things will dissolve. There's only a few instances where that's not true, that increase in temperature decreases dissolving of solids. Gases is the other way around. Increase in temperature means less dissolves. And that's because gases are more entropy favored than liquid. So, but supersaturated. So most things are unsaturated. Like when you have solutions, it's more likely than not, it's going to be unsaturated. Has anyone ever made brine before? Like actual brine? It is crazy how much salt dissolves in water. So brine, like brine is saturated. I guess it depends on your definition. I would call brine saturated salt, sodium chloride salt. Some people might give it like 10% or something like that, but it's 3 to 1. It's a 25% by mass solution is about where salt dissolves in water. And although salt is about 3 times the density of water, so if you have 100 milliliters of water, you need about like 10 to 15-ish milliliters of salt. I guess it'll be closer to 10. It'll be like 10 milliliters of salt. That's a lot of salt. I mean, you start pouring the salt in there. It's amazing how much salt you can get to dissolve in water. Like, because I've made saturated solutions for lab. It's just like, man, and the way that you can tell that it's saturated is that nothing else will dissolve. So so it's just like, I was always thought, like, man, this stuff dissolves really, really well in water. But so that's saturated. Unsaturated, like I said, most things, if more dissolves, it's unsaturated. And then supersaturated, do you guys ever eat rock candy before? So how you make rock candy is you take sugar, sucrose sugar, and you make a supersaturated sucrose solution. And then you put sticks or strings into that supersaturated solution and/or flavoring. You probably, but you have a supersaturated sugar sucrose solution, and as the solution cools, sugar crystals grow, and that's rock candy. That's how you get rock candy. It's from a supersaturated sucrose solution. So, and here's the solubility of different salts. So if you look at the y-axis, this is the solubility of I thought it was 25%. It's 35% for sodium chloride. Sorry about that. But solubility of salts in water on the y-axis, and the x-axis is temperature. You can see in virtually every single case, it goes up. And I'm not sure why cerium sulfate decreases with the temperature, but basically everything else goes. You can see sodium chloride's fairly flat, but most of the other ones, they go way up with temperature. So that's when you can really have a supersaturated solution. Okay, questions? Okay, so that's solids. What about gases? So unlike solids, you increase the temperature, the solubility goes down. And the reason is because of the T delta S term. So because gases have more entropy than liquids, and so a solution is, in this case, an aqueous solution, liquid solution. The entropy favors the gas. So if you increase the temperature, you favor the gas leaving. And pressure, if you increase the pressure, the solubility goes up. And then there's Henry's law. This is Henry's law, and really interesting. Henry, among other things, worked with another, I think Hildebrand, for scuba diving, and figured out that one of the ways to avoid people getting the bends is to put helium into mixtures rather than nitrogen. But anyways, Henry's law says this S, the solubility of a gas, is equal to the Henry's law constant times the pressure of the gas. And to give you an idea, so, and this is, I mentioned before, a lump sum approximation. This is just the lump sum there. Okay, so what pressure of carbon dioxide is required to keep the carbon dioxide concentration of a bottle of club soda at 0.12 molar at 25 degrees Celsius? So the way we actually make soda is we take carbon dioxide and we pressurize it. So solubility, okay. So what we do is we solve for pressure. So Henry's law, solubility is Henry's law constant times the pressure. So we're going to solve for pressure. Pressure is equal to the solubility over the Henry's law constant. And the solubility is 0.12 molar. That's our target. And the Henry's law constant is 3.4. So I'll go ahead and put the fraction in. 0.034 molar per atmosphere. And so notice the units, the molars cancel, and 1/1 atmospheres. And if you do that, this is going to be 3.5 atmospheres. So if we want to have soda water, we have to charge it with 3.5 atmospheres of pressure. And have you ever made or ever seen someone make soda water before? They have machines now you can do. You can do carbon dioxide and they pressurize it and you can make your own fizzy water. So I don't have one of those, but I do like fizzy water, but I did some calculations like how much the carbon dioxide costs and versus just going to Safeway and buying the cans and or bottles. And I was like, I'd have to consume something like 100 bottles, 100 2-liter bottles of fizzy water a year to justify a tank of CO2. It's like, I'll just go to Safeway. So, but the way that it works is when you make the soda water, and this works for many other beverages too. So there are some beverages that you make that the fermentation actually is where you get the fizz from. So it's not just alcohol, although beer and champagne can be made that way. But one time I was making actually more my wife. She wanted to start making her own ginger ale, and so we went and we made something called a ginger bug. We bought some organic ginger at the market, and then if you grind it up and you feed it sugar, it turns on the ginger bug, and then it becomes like a pet. You have to like feed it sugar, and then you can take the sugar and put it into more sugar water, and then if you add something, you make your own ginger ale essentially, and it worked really well. It generated its own carbon dioxide. It pressurized it so you can make soda water that way. So, but you can do it like what most of the time we do is we actually just go and we just charge it up. But then it at 3.5 atmospheres, it reaches the 0.12 molar concentration. But then when you open up the bottle, right, when you have a sealed bottle and you top the lid, like the cap, or you turn the closure, it goes like, right, your head, and then the fizz comes out, and all the bubbles come out, because it went from a pressure of 3.5 atmospheres to 1 atmosphere, and then it's thermodynamically unstable, so then the bubbles come out. So that's also, and you also know that they're under pressure, right? If you take a bottle of soda and you hit it with a screwdriver, it explodes, right? So, or at least it squirts out, and that's because it's under pressure. So let's see if we can figure this out. What is the concentration of ammonia when the pressure of ammonia is 0.1 atmospheres and the solubility is pressure time, well, I guess it was backwards. Henry's constant times the pressure, and it changes for different gases. Some people think A, some think B, some think C, or D? Okay, so you're still thinking solubility is going to be 58 molar per atmosphere times 0.1. Okay, hopefully it's easier than you thought. Hopefully you can see it's B. I guess you didn't. It's just a quick plug and chug there. Okay. So next thing I'm going to talk about is different concentration units. Or does anybody have any questions with Henry's law? So it's pretty easy. It's just right. You have one equation, solubility, Henry's law constant times the pressure, and it's going to be one equation, one unknown. So you might have to rearrange the equation like this problem, or it can just be a straight shot. Or unless you're finding out the Henry's law constant, that's the other thing you can look for. And they change for different gases. You have a question? K stands for constant. And in this case, it's the Henry's law constant. So that's the K sub H. So this is, if you remember, I was talking about semi-empirical models. This is a semi-empirical sort of empirical model. It's a specific something called the lumped sum approximation, where you just take all the stuff and you throw it into one value, and then you figure out where it works in a certain range, and then you just manage the error. So friction is the most common, the easiest thing to talk about that I mentioned before. So this is the Henry's law constant. It's a lump sum approximation, semi-empirical model. Yes. And you'll be, I mean, unless you're looking for it, you'll be given the values. So here, okay, that's good enough. So like right here. So you can find them in tables, and you'll be given the values. So other questions? And you can notice the units are in concentration per pressure. I know that the glare is on that. The units are molar to atmospheres. I mean, you might see something like, I don't know, molar to inches of mercury, I don't know, or grams per milliliter per torr, just watch the units. It'll be concentration per pressure. So other questions? For this class, it'll be molar per atmosphere, but if you are, when you're out and about in the real world and or another class, you might have different units. So, okay, so here are some other concentration units. Molarity, you're probably familiar with, is moles per liter. Molality is another one. Molality, it's the amount of solutes in moles, so what you're dissolving divided by the solvent, and the mass of the solvent in kilograms. So coming up next class, there are certain things that we use molality for as a concentration unit. Mole fraction, X, this is the amount of solvent or the amount of solute in moles over the total amount of solute, the total moles. The moles of whatever of the total moles. And so no units in that, it's just the moles cancel. Mole fraction, I might want to also clarify, in everything except for chemistry, X usually refers to the mole fraction in the liquid phase. Y more commonly refers to the mole fraction in the vapor phase. So you'll see that especially in the CFRs, the Code of Federal Regulations, CFRs. If you ever, I remember one time someone came to me and was was wondering about some units. So it makes sense. I don't understand these units, so they came like, I'll go ask the chemist. And we were looking in the Code of Federal Regulations, and they were dealing with something called with emissions, and person was like, what does this Y mean? And it's like, oh, it looks like the mole fraction, but it's a gas, and everyone else uses, at least in like engineering, we use Y for the gas phase. So if you ever have that case, if you're in engineering and or if you look in the Code of Federal Regulations and you see Y, usually it means the mole fraction in the gas phase. So mole percent is just the number of mole, it's the mole fraction times 100%, is all it is. Mole fraction times 100%. Parts by mass, you have the mass of whatever over the total mass times your factor. If it's percent, it's 100. If it's parts per million, it's 1,000,000. If it's a billion, parts per billion, it's a billion. So meaning so percent really means parts per 100. So if I'm 30% body fat, I don't think I'm 30% body fat, but it means that if I have 100 grams, 30 of those grams is fat. So 30 divided by 100 is 30%. And then I'm 30 parts per 100 fat if I'm 30% body fat. And parts per volume is the same thing as parts by mass, except it's by volume. In liquids, a lot of times we use parts per volume. And alcoholic beverages, for instance, we use proof a lot of times for that. Proof is just double the percent by volume. So if it's 80 proof, it means it's 40% by volume, which means if you have 100 milliliters, it's 40 milliliters of alcohol over the total solution. So anybody have any questions with that? I'm going to go into an example. Actually, I wonder if this is a good place to stop. It might be, because I don't think I can get through this in 5 minutes. Yeah, I'll pick up here on Wednesday. But I will give you a preview to Wednesday, because Wednesday we're going to go into colligative properties. Colligative properties are things that depend on the number of particles. So, and those qualities are vapor pressure depression, freezing point depression, boiling point elevation, and osmotic pressure. So certain effects happen in solutions, and it depends on how many particles that they have. And so if you have a molecule like ethylene glycol there, that's one particle. Sugar stays together, sugar is another one. Sodium chloride breaks apart into 2 particles. Magnesium chloride would break apart into 3 particles. So like iron 3 chloride would break into 4 particles. So, and what the effect is on the effect of these things: vapor pressure depression, freezing point, boiling point, and osmotic pressure, they change based on the number of particles. So I think I'll stop there and have 4 minutes of your lives back, unless anyone has any questions about anything. And the questions are fun. I always find them fun, but the warning is, and the new students, I have a bad habit of giving dollar answer to nickel questions. So if you ask me a question, I will tell you more than you ever wanted to know. So, and I do talk about some things outside the scope of the class, because I'm trying to inspire you to take more science classes, among other things. But I also try to ground you, to let you know, like, okay, this is what you have to know, kind of stuff. And I know I flew through Henry's Law, but Henry's Law is pretty easy. All right, well, I'm gonna go ahead and stop. I'll go ahead and post